Okay, this is an example of using Snell's law. Right? Remember, Snell's law is a relationship used for a wave that's refracting as it's passing from one medium into another. So Snell's law is n1 sine theta 1 equals n2 sine theta 2. Right? So the left-hand side of this equation is the medium that you're starting in, and the right-hand side of the equation is the medium that the wave is traveling into. Right? So this is your starting medium. So these are all the values for your starting medium. And the right-hand side is the medium that you are traveling into. So this is the entering medium, we could say. Right, so I'm just going to take you through one example, and in particular this video is going to show you how you actually measure and draw the angles. If we were in the classroom and doing the actual labs, we would be actually measuring and drawing refracted and reflected rays as they travel from one medium into another. So to do this, we would be using protractors and rulers. Right, and so what I have done is just printed out a protractor. I can't find my protractor at home, but I printed out a protractor just from the internet. And I'm just going to use this to draw the boundary. So I'm going to draw the boundary between two mediums just as a straight line. I'm just going to use this to draw a somewhat straight line. And so this is going to be the boundary between my two mediums. So let's have a light ray travel from air. And let's have this actually go into a piece of glass. So, for example, if you had a piece of glass, let's see what I can find quickly here. I have a prism here, right? And so what we could do is, prism is not the best example, but I don't have just kind of like a slab of glass hanging around. But what we would do is take a material and set this here and actually look at the way that the ray refracts as it travels in. Now, what's interesting with what I've just done here is you can see that my light is refracting through this piece of glass, this prism, because you'll notice that the line that I've drawn doesn't stay straight as it travels through that prism, right? It looks like it kind of bends a little, right? It's distorted, and that's what refraction is all about. Right? So that's just kind of an example to show you why this is actually really important. So let's go from air, let's go into something like crown glass. Okay, and so when we draw this, the very first thing that we need to do is draw the normal. Okay, all the angles get measured from the normal. So remember, the normal is a line that's perpendicular to the surface. So I'm going to draw something that's perpendicular 90 degrees to this boundary. Right? So I'm going to take my protractor, and this is going to kind of go off the paper here. But what I'm going to do is just line this up, and I'm going to place a dot way up here, kind of off the screen, where this falls at 90. I'm also going to do the same thing below. So this is just showing me where, I guess I need like a reference point here. This is where we're going to start. So this is my reference point. And we want this to be at 0. Right, so here's my 90. Right, and so luckily I can see through this paper. I can see that line. Let's just make sure this is line. There we go. Perfect. And here's my 90. So what I'm going to do is just draw my normal, and I'm going to have it go from the air into the glass. Typically I draw the normal as a dotted line. Okay, and so this is 90 degrees. Right. So then I'm going to draw my light ray traveling in. So let's have the angle of incidence be equal to 30 degrees. So I'm just going to write this over here. My theta 1 will be equal to 30 degrees. And so what I want to know is the angle of refraction. So we want to find theta 2. So if we have a light wave traveling into a piece of crown glass, and it's incident at 30 degrees. How much will it refract, right? That's our question here. So I'm going to take my protractor, and I need to draw my light ray coming in at 30 degrees. So again, I got to line this up with my 0, right? This is where my 0 would be on the protractor. This is angle 0. Make sure my 90s are lined up. And we're good there. So I'm going to just make a mark 30 degrees from the normal. So 10, 20, 30. So that's going to be right here. So I'm just going to use that as my reference point. And then I'm going to use the straight edge to draw my light ray. So from here, here is my incident light ray. So this is theta 1 at 30 degrees. Right? And so if you go remeasure that, that should be a 30-degree angle. Right? Very nice. Right? And so now here's where we calculate. So we actually have to calculate theta 2. Right? So we're going to use n1 sine theta 1 equals n2 sine theta 2. Okay. So n1 is air, so that's just 1. Sine theta 1, so sine of 30 degrees, equals n2. So now I have to know the index of refraction for crown glass, which is, if you look at your reference table, is 1.52. So this is 1.52. And then we're going to calculate theta 2. All right, so when you do this, you want to make sure that your calculator is in degree mode. Right? If you're getting answers that are different than mine, that may be your mistake. Right? So make sure that you do that. And you want to make sure that you're actually solving for theta, so you have to take the inverse. And I get an angle of 19.2 degrees. Okay? So that tells me that this light ray is going to refract at 19.2 degrees. So now it's going to refract into the glass. Okay? So 19.2 degrees from the normal. So whatever angle I draw, right, where my light ray comes in, it's going to be measured from the normal. So I am going to take my protractor, I'm going to flip it around. Right? I'm going to line this up so that my 0 is right at the angle of incidence. Again, it's hard to see, right? I have to be essentially looking through the protractor. Luckily, I can kind of see through it. Right? Line everything up. And then from the normal, which is at 90, I'm going to measure over 19.2 degrees. So here's 10, here's 19.2, so somewhere right here. And then we draw, our light ray. Right, so here is theta 2, and that came out to be 19.2 degrees. Right, and so you can see it does not follow a straight line as it travels in. Right? It refracts and it actually bends towards the normal. Right? So theta 2 comes out to be a smaller angle because it's bending towards the normal. And that tells us that the wave actually slows down. Right? When light bends towards the normal, the speed is going to decrease. When it bends away from the normal, the speed is going to increase. The other thing to make sure that you are always thinking about is, yes, light will travel from air into glass. Part of it travels into the glass. There's also usually always a piece that reflects as well. And so we also need to include that reflected angle. And so we know that using the law of reflection, my angle of incidence will equal my angle of reflection. Okay, and so we do need to draw that as well. So I'm going to draw my reflected ray that reflects off the surface back out into the air. So that was 30 degrees. So line everything up. 10, 20, 30 degrees this way, and we draw. And so this angle here is my angle of reflection, which is equal to 30 degrees. Right? And so those are the diagrams we would be drawing. Sometimes you'll be given the refracted angle and you would have to determine the angle of incidence. Sometimes you may be given both angles and have to actually determine the index of refraction for one of the materials. But that's Snell's law.